Swayam Prabha. Digital India. Educated India.
What do we do in main? We call printf the function. So do you think the printf definition would be there in the obj dump? Yes, no? There can be two answers, yes, no. How many say yes? Okay. How many say no? The rest, I guess, right? Or is it, I don't know, I want to play safe? Okay. So let's assume for now that the definition is in there, right? And let's go look for it. How do you do that? Obj dump minus d hello. What is all of this? Okay, where is our main now? Did we write all of this? Did we write underscore init or dot plt? I don't even know what that is. What's puts plt? Puts @plt. There is underscore start for some reason. Deregister tm clones. So these are all function names, right? Deregister tm clones. What does that even mean? Register tm clones. Do global detours aux. Frame dummy main. Finally, right? Finally, we got main. And what does a call queue transform to? Because that is what we are interested in. What does it transform to? It transforms to an actual address, right? And what is that address in angular brackets? That's puts @plt. There was puts. We knew puts was going to be there. What's the @plt? Let's look at puts @plt. What address is it at? 4003 F0. That is 4003 EC F0. It's here, right? This is puts @plt. Okay, so you don't need to be a genius in reading assembly code. Okay, can you guess if this prints a string? Does this print a string? Yes or no? Yes, but it is just jump, push, jump. How would a jump, a push, and a jump print a string? So you're jumping to some point, then you're pushing something on. Well, it's literally 0 onto the stack, and then you're jumping again. How does that print a string? What would you expect when you're printing strings? You'll probably expect a move, and you'll expect some other things that we'll talk about later, right? A jump, push, and a jump is not a string printing function. Ergo, this is not puts. Okay, this is not the real puts. It is puts @plt, and we have no idea what that is. Okay, actually, we do have an idea what that is. You must have done your systems course, and you must have talked about, you must have learned about position independent code, right? Position independent code doesn't ring a bell. Never heard of it? Okay, fine. So when you are compiling a program, you say I want to call a function puts, right? What is a function call essentially? It is a call to a certain address, right? When you are loading that program in memory, you need to know what that address is, correct? For that, you need to know where puts is in your address space. Okay? If you were all in one binary, you would know where that is. You'll find the offset, and you'll be able to jump to that address. If you don't know, as is the case over here, puts is not in here, right? There's only one stub. It's called a trampoline. Okay? There's a trampoline which allows you to jump to push. Okay? So now what the code that the linker generates, it generates a trampoline and a jump to that trampoline, and it says somehow now that is going to result to a jump to puts. Okay. Who does that jump? We will find that out later. You had a question? The question was who does that jump? No. Okay, fine. Right. So, there is another aspect to it. Linking. You must have heard of dynamic linking versus static linking, right? So, what do you think this is? How many say dynamic? Okay, and I am assuming the rest of you all say static, right? So, this is dynamic. Okay. The main feature of dynamic linking is that when you are calling a function which is in a different library, you have a trampoline here, okay, and you do not have the actual function. The actual function might be anywhere, and that is where position independence is required. Okay. And you will appreciate this much later when I show you how a process looks like in a computer, right. Now, this is dynamic linking, then let us look at static. Okay. How do you produce a static binary? Okay, before we do that, let us take a look at hello in terms of size. How big is it? It is 8 kilobytes, right? Okay. You are doing that also, right, on your systems. So, it is 8 kilobytes. Now, let us build it statically. The way to build statically is to use the minus static flag. Okay. Once you do the minus static flag, you look at the binary. What is the size of the binary? It's the same? It's 700 kilobytes. It's 100 times bigger, right? It's 100 times bigger now. It obviously has 100 times more code, right? So, let us take a look at it. And this time I won't do any gimmicks, I will just jump straight to main. Oh, by the way, this init and all, I will talk about it a little later. Here's your main. Okay. And now look at your call. The call is, it's not puts, it's what? IO underscore puts. Okay. The reason why it is IO underscore puts is because that is the internal name for glibc. Okay. So, glibc uses the IO underscore puts name so that it does not have to jump through a trampoline. If it calls puts, then it will have to jump through the trampoline. So, it calls its internal name IO puts, so it goes directly. What is the disadvantage of jumping through the trampoline? It is an extra instruction, right? It is an extra 3 instructions, CPU cycles, right? And in fact, there are other aspects to it as well. Your PLT would be here in memory, your IO puts would be here, and my function call would be here. There is something called as cache locality, right? Whenever you are making a call, you make a call over here, it does not mean that this is going to be cached, only neighborhood stuff will be cached, right? So, there are a lot of things that make it much slower to do that indirect jump. So, these are called indirect calls. Okay. So, to avoid that, we use the internal name. So, now let us look for IO underscore puts. Here. Now, this is a very, very big function and is much likely to be a print, right. So, it is all the way up to here, right, 40841B from 408.140, right. That's a proper massive function that does stuff. So, you can, if without actually getting into the assembly, you can assume very safely that this may be printing an array onto a screen, a string onto a screen, right. So, now here is the interesting thing. You linked statically, so you got the entire function over here, right. You got the entire function in there and it's there in your binary. Now this binary does not need libc. The dynamically linked binary needed libc. Okay? So the way these programs are executed are also very, very different. This static program and the dynamic program. Right? Any questions up to now? This is all we've done to find out what happens to your C code right down to your final program. Okay? Now we'll look at the program a little more closely. Okay? And to do that, we're going to try and write the smallest program possible. All right? What is the smallest program that you can write? Hello world is obviously not small. If you pre-process, it is 844 lines. What's that? Empty program, just int main, right? So I'll cd into another directory. There you go. And now this is what you're talking about, right? You can return whatever you want, but essentially int main and return your favorite number, right? Do this program and generate a binary. So how do you test the return code that your program is given? It is returning 42, right? So how do you test that? So in shell, once you execute, you have an echo $?, which queries the previous program's return state. Okay? So now you know how to check if the program is working correctly. All right. So now this is a really small program where the first function that ever executes, which is main, right, in your program, that's the first function that executes. It returns 42 and it exits termination. It exits the program, right? That is so simple. It should be, when your compiler is trying to optimize it, it should produce what, 5-6 lines of assembly, right? There should be nothing more than that, nothing at all. Now let's see what it actually generates. So how many lines did it generate? (151) lines of assembly. Right? So to figure out at what stage all of these lines got added, let's first generate only the assembly code. Okay, so this was what our main looks like. Let me just produce the obj dump because it's easier to read. Okay, so this was what we were expecting, right? We were expecting main, and main is the first function that gets executed, right? And that's it, right? There should be nothing else. Why is the compiler, so the compiler is working fine, why is the linker adding so many things? Any clues? So when the program is executing, right, if I look at obj dump, why does it need all of these things? Okay, why doesn't it stick to just main, which I can't even find? Here it is. Right? It is just this much. What is all of the other cruft in there? And is it necessary at all? How many of you think it's okay? How many of you think it's not necessary and we can get rid of it? It's necessary? You always need that? But main is the first function that executes, right? Yes, everyone agrees. Anyone who disagrees with that? Okay. So now let me break it to you. Main is not the first function that executes in a program. When you write int main, that is just a C language standard that says that int main is where your your business case as such starts and ends. There are a lot of other things that start before that, and as such for every program there is a symbol called _start, which is the beginning of your program. Okay. Again, I have lied. _start is where your program starts, but then there is something called as _init, which initialize your program. Okay. So when you look at this, you have an _init, which initializes your program. Okay. It is an initializer. Okay. And then you have _fini right at the end, which finishes off your program. Okay. So there is a more modern concept called init array and fini array, which allows you to provide multiple initializers and finishers to your program. Okay. Now, if you look at programming concepts, what is a concept that is parallel to this in OOPS? Constructors and destructors, right? So this is essentially your object destructor, and this is your object constructor. So when you're writing C++ programs and you have an object, right, which has to be constructed on program load or whatever, or destructed, it will typically have an init array function in there. It will be a function in an init array section, right. So you have your init and fini, your constructors and destructors, even in low level programming, because they are necessary to implement whatever high level construct you think of in your program expression, right. And once your initialization is done, then _start, and then at the end, once your program is over, fini is called. Now, who calls all of these functions? Right, that is the next question. Who calls _start? Who calls _init? Who calls _fini? We will leave init and fini aside. We will look at start. First, a quick detour for the smallest program that you can write. This is the smallest program you can write. Okay. Type this. Right. So all of the spaces that you see are tabs. Okay. Your assembler, it does not strictly require that, but it is nice to write it this way. And this also introduces you to a new instruction called syscall. And there is no ret over here, if you have noticed. So the first number that you move into RDI, it can be any number. The second number, make sure that it is 231. Yes. It could be properly spelled as global as well. It identifies both. So some crazy person in the 70s decided GLOBL was right, and it is stuck. It stuck as a compatibility thing. Okay. So how do you build this? Let's build this using the assembler AS. Okay. So we are like completely bare bones now. The next thing you would be doing is typing ones and zeros. We could actually do that with this program, right. So AS tinyasm.o tinyasm.s, okay, and then LD tinyasm.o, okay. Then when I run my tinysm, it gives me the right output. Okay. Now, if I look at all of the files, smallest was 7.8 kilobytes and tiny ASM is just 700 bytes. Okay. So, that is what we were going for. We were going for a very, very, very tiny program, and we have achieved that with tiny ASM. Okay. Does everyone get this? Anyone who's stuck? Do you need help there? It's done? Couldn't find entry symbol start, right? That's probably because you did not write dot global start. This line, let me see. This line. In any case, that's a warning. Okay, so you'll get the final output. Sorry? Dot global. Dot global space underscore start. I'll need to figure out the syscall numbers for it, but so I can tell you the syscall numbers. That's not sufficient. Yeah. Yes, that's not sufficient. But then that's a good point. So I'll show you how to find the syscall number, and then you can fix up that program. Okay. So I assume everyone's got this. So let's step through the program. Okay. And there's not a lot to step through. There are just 3 instructions. What does the first instruction do? What does it do? Move 42 to RDI register. Okay, that's your function call ABI, right? Except that this is not function call ABI. This is sys call ABI. Okay, the sys call ABI or the system call ABI is different. Everyone knows what a system call is, right? What is a system call? Which system? Operating system. Okay. You were saying something. Okay. Right. So, right. So the way, okay, when you say operating system, you have to be very, very specific. It is the kernel that you need. You're referring to, right? And why do you need a separate system call infrastructure for the kernel, and why can't you do something like a function? Because with libc you can always call a function, right? And the function ABI, function call ABI is sufficient. So why do you need a system call ABI for this? And why do you need a special instruction called syscall for that? System call number is right. We are pushing that number in RAX. See, this 231. There is a system call number which tells you which service I need, right? And then I say syscall. But why do you need such indirection? Why can't you just call a function inside the kernel? Right. No, I'm saying at the ABI level. Why don't you just do call exit underscore group? This syscall number is exit group. Okay, 231 for 64-bit. As she discovered, for 32-bit, it's a different syscall. Okay, so you need to figure out what that is. Right. So why do you need to do that? Why do you need to set a syscall number in RAX and then call a separate instruction altogether called syscall? And why can't you just do call exit underscore group? But what is special about the kernel? Why couldn't I just link the kernel as a library and make that call? I am asking you why they cannot be called. I know they cannot be called. Sorry? Privilege level, right. That's what I'm looking for, right. So, whenever you are executing code, you can either execute in user mode or you can execute in kernel mode, right. What is the difference? User mode has a specific set of addresses that it can reference, right. It cannot reference anything outside of it. It basically has an abstraction of its own that it can use for accessing objects. It cannot access anything inside the kernel, correct. So, you need to provide a special instruction called syscall. In 32-bit days, it was a proper interrupt. It was int, interrupt number was 0x80, right, and that interrupt handler was written in the kernel that would then execute the syscall, right. It would read the syscall table and execute whatever syscall is required, correct. You need all of that for privilege separation. Okay. Now, how many of you are interested in security? Right. So, most of your security bugs when it comes to privilege escalation is essentially trying to defeat this barrier. Okay. How many of you are interested in cloud computing? Awesome. Now, when it comes to cloud computing at a processor level, it is essentially just a privilege barrier. Okay. Now, this was now in ARM terms, because I do not remember the x86 terms. x86, I think there are rings, ring 0, ring whatever, right. So, in ARM terms, you have EL0, exception level 0, which is user mode, exception level 1, which is kernel mode, and then there is exception level 2, which is hypervisor mode. Okay. So, now there is also something called as exception level 3, which is called secure boot mode, right. So, these are different privilege levels, and the idea is to never cross those privilege levels, and you always write code within those privilege levels, right. So, when you are writing virtualization hypervisors, you are writing it in EL2, okay. You are writing code that executes in EL2, and then when you want to execute a certain kernel, depending on which kernel it is from different guests in virtualization, you execute those in EL1, and then for user space EL0 for that kernel, that process. Okay. So, you have all of these levels of security abstractions for that very reason. So, syscall is one way to do it. There are similar instructions to switch between privilege levels between EL1, EL2 as well, and EL3. Okay. So, this was the smallest program that we saw. Now, to discover how these programs actually execute on your machine, right. Now, I showed you that main is not the first function that gets executed. It never was, it never will be. I had mentioned early initialization. I do not know if anyone actually noted that down. So, early initialization is essentially underscore init and whatever happens in underscore start. Okay. A bunch of things happen in underscore start, and then main is called. Okay. And those bunch of things, we will probably take a brief look at that. All right. So, the next thing we will get back to hello. Okay. And so, when you are looking at the static program, okay, let us look at, I do not remember which program this is. So, if I use the file command, so it gives me information about that program, right. So, what does it say? It says a 64-bit ELF LSB executable whatever version 1 statically linked. Okay. So, I have a statically linked program, all right. Now, if let me just build it dynamically, and I will call it hello.din. Okay. This is why -o is always important. You should always keep it. It is a practice, right. It is a very good practice to have. So, now I can compare them side by side. Now, this is dynamically linked, right. And here is the interesting thing, it is dynamically linked, and then the interpreter is this, and this is very, 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 very important. Okay, and it defines how your program is going to be executed. Okay. Now, do you know the system call that you would call to execute a program? The set of system calls. So, you have fork, which creates a new process, which is an exact image of the parent process, and then you call execve, right. So, what does execve do? Fork creates the similar image, right. What does execve do? Load the new program, right. So, it loads the new program in memory. So, where does this happen? Does it happen in kernel mode or user mode? And is loading the program sufficient? Okay. So, do you know the operation is called loading? And when you think of in system software, you have compiler, what is it? Compiler, assembler, linker, and then loader. Okay. So, now we are going to look at the loader. And the loader is not just one. Okay. There are two parts to the loader. Okay. The first part is the kernel, and for that I will open up the Linux kernel source. Okay. How many of you have downloaded this kernel source? If you haven't, you should go home and download this. And for every assignment, every concept, try to discover that concept in Linux. It's not that hard. Okay. So, in the kernel, there is something called as fs/exec.c, which is what provides the implementation for execve. Now, what exec.c does, and I expect you to look at this once you get home or in your lab session, is that it loads the program and it starts reading the program. Okay. And the program is what? It is a file. It is a binary file, correct? And to be able to read a binary file, it needs to understand that binary format, correct? So, now if you look at fs, you will see bin fmt underscore star different files. Okay. Do you see a out over there? That is your a.out format from many years ago. Okay. Nobody has a.out format anymore, as in there are some maybe atomic reactor computers from the 60s or 70s which probably have a.out format binaries, but almost all of them today are in ELF format. Okay. So, the exec function will read using the ELF format decoder, okay. And the first thing that it will look for is whether the program has an interpreter or not. Okay. And this should blow your mind. You used to think that C was a compiled language and there is an interpreter for that, right. And it is a different level of interpreter, it is a different kind of interpreter. That interpreter is essentially the loader stage 2, as it were, okay, and that is implemented in glibc, right. So, if there is nothing of that sort, then it will look at the underscore start symbol inside that binary, and first it will look for the init section, run all the initializers, underscore start, and then start of the execution from there. Okay. So, it will transfer execution to that pointer in memory and go into EL0 and execute. Okay. So, that is fairly straightforward. It is when it finds an interpreter that things get a little interesting. Okay. When it finds an interpreter, it will execute the interpreter. It will load the interpreter in memory, okay, along with the binary, and then it will execute the underscore start of the interpreter. The interpreter does not have an, it has an init. So, it will do init, but it is very rudimentary, and then it will call the underscore start of the interpreter. And then from that, the interpreter takes over and it does a lot of very interesting things, which we will look at one by one. So, this was inside the kernel. Any questions here so far? None? All right. So, we will go back to glibc now. Now, glibc is where, so okay, there is a lot of stuff. So, there is a directory called ELF, which has, okay, this is also a lot of code. So, the ELF directory has the dynamic linker, okay, and the entry point for that is in a file called rtld.c, but the underscore start is architecture specific. Okay. So, it has to be written in assembly code. So, there is a file called dlmachine.h, which will be sysdeps. I will show you ARC64 because that is what I remember, but then there is an x86-64 version as well for this. Right. So, now remember that 4-line underscore start that we did, this is not very different there. So, this is your start. Okay. So, it is actually only this much, okay, and then it calls something, then DL start user comes in again, and essentially what happens is that the dynamic linker will then start reading the program again, okay, the program that you executed, all right, and it will start reading the library dependencies. It reads the libraries that the program needs. How do you find that out? You use a command called LDD. Let us look at ls, since that is our favorite program today, right. If I say LDD, it says all of these programs it depends on, all of these libraries it depends on, right. So, the dynamic linker does the exact same thing. It reads that binary, okay, and it reads all the dependencies, and what does it do? It loads each of those program libraries in memory, okay, and then for each of those libraries it will call its constructor, okay. And once that is done, once all of this is done, because now you can imagine there is a library in here which might be using another library as well, okay. So, that becomes essentially a dependency tree. So, it has to resolve the dependency tree. Once all of those have been initialized, then your program is initialized, okay, because it is assumed that your program cannot run without all of these libraries properly initialized, correct. Lot of things can go wrong over here. You can even have circular dependencies. In fact, there is a real circular dependency inside glibc. There is a library that implements threads. So, the threads and libc proper are circularly dependent on each other, and we have some dirty hacks in place to make sure that they initialize properly. So, you have like partially initialize in one place and then initialize the other, right, and then there is some redundant initialization which happens inside libc as well as libpthread. In any case, so all of this initialization happens, and then a function called libc start main is called, okay, and once that libc start main is called, that locates the main function inside your program, and it calls that main function. So, after your main function exits, it comes back over here inside libc start main, then it runs all of the destructors, and then it does the exit group syscall. So, that is how your entire program executes. So, it is not just your main, right. There are a lot of these things before and after, right. Any questions so far? No? Okay, great. So, now we will proceed to the next part, which is actually seeing your program in memory. So, now you know how it is compiled into machine code. I assume you understand everything of that. If you do not, you ask me questions. Then from there, we looked at how it is loaded in memory, right. There is one command that you can very easily use to see how your initialization happens, right. So, there is an environment variable called ld debug, and if I write file, if I assign file to it and I say hello, this is also why you should probably be using Linux when you are studying, right? Because there are a lot of things that you can just explore, and you can just start looking at the source code and try to figure out what is going on in there, right? So you say ld debug equals file hello. Once you do this, no files. Oh, this is a static one. Sorry, there. Okay. So what does it do? Let's just walk through this. Right. So hello is very simple. It uses only libc, right? So it sees libc.so.6 needed by hello.din, right? Generates a link map for it, meaning it parses libc.so, right? Then it looks at the parts of whatever. Then it calls init for libc.so. Then it inits hello.din. Then it transfers control, and then it calls fini, right? So if you look at something a little more complex like ls, it looks a lot bigger, right? So it looks at libselinux.so, then libpcap.so, then you have libc.so, libpcra2, dl, pthread, blah blah blah, and then so at this point it's created a dependency tree, and it's flattened that tree to make a sequence of initialization, right? And then it calls the initializers. So first one is pthread, then libc, then dl, pcre, da da da, and then finally bin ls, right? So all of these things happen first, and then your program executes, right? Then there is something called a symbol resolution, which you can say all, and then it will look at all of the symbols. Okay. So symbols are essentially your function calls. So you called printf, for example, right? Now where is printf? Now you provided a declaration for it, correct? On one machine you provided a declaration for it, and you were able to compile it. On another machine you were able to link it to a library, but now you want to run it on a third machine. What is the likelihood that printf is there? There is no guarantee, right? So what the dynamic linker does is, when it encounters an unresolved symbol, meaning that symbol does not have an address in that entity, it will look in all of the libraries that it is linked to, libpcap, libc, pcre, dl, so on and so forth, and it will look for the first instance of printf. Okay, so the moment it finds the first instance of printf, it will record that address, and this is how relocation happens. This is how position independence works. The @PLT, that @PLT is essentially a table. It is a jump into a table. So that table is filled up, saying that, oh, I found printf, it is at this address. So whenever I am jumping, I jump from here to that address then, right, after that table has been filled. Now there is an obvious hack over here. Now if you want to override printf with your own printf, all you have to do is write a printf function, build it into a library, and make sure that it is the first to load. Okay, so if it is the first in this sequence, okay, in all of these, so from libselinux downwards, if it is the first one in that sequence, then your printf will be caught first. Okay, and this is called function interposition, and it is a very useful tool. In fact, all of your low level debugging, function interposition is probably the most important tool that you should learn. Valgrind, vagara, everything is later. In fact, some of them even use function interposition as a concept to debug programs. Imagine if you want to gather statistics of how many times your program calls the printf function, or how many times your program calls the memcopy function, right? Let's say you are doing it in a loop, okay, and you want to gather statistics for that. You can use interposition for that, where you you make an interposition function which increments a counter and calls the real function. Okay, does that make sense? Great. Right, now we will move to actually visualizing your program in memory. Threads. Okay, so how many of you have written a multi-threaded program? Okay, so you've written pthreads functions, right? So we'll be writing a simple pthread program later. First thing is you need to figure out how your program is laid out in memory. How do you do that? There is a very simple way on Linux. There is a file system. It's a pseudo file system. It's an in-memory thing, structure that Linux abstracts, called the proc file system. Okay, the proc file system gives you a lot of information about your kernel. Okay, you can even tune the kernel using the proc file system. Okay, so the easiest way to find out or visualize how your program is laid out in memory is to read a file called maps. Okay, and this is a special hack where you say for the process ID, you say self, meaning yourself, whichever the program is. Now, cat is the program over here. All right, cat is reading itself. Okay, and this is what cat looks like. And this is very big. Okay, yeah, right. And what is this? These are address ranges, permissions, and what file is on it. So now, if you look at cat, cat not only has 3 different segments. So if you look at this, there are 3 different portions of memory for cat with different permissions. Not only is that in the address space of cat, you also have libc.so, you have something called as local archive, which I will not get into, ask me later if you want to, and then there is a dynamic linker, and then there is something magic here called stack. Right? When you say stack was on RAM, it literally is there. It's this notional concept which is there in memory, right? And these are the memory address ranges within which it is there, and it is read write. Okay? And then there's something called as heap. What is the heap?